on weight. Anything thrown up falls downwards towards the earth. Climbing upstairs is a lot more tiring than walking downstairs. Raindrops from the clouds fall to the earth, and all of this happens because of the Earth's gravity. It was Galileo who recognized that all bodies, irrespective of their masses, are accelerated towards the Earth with a constant acceleration. He said that all objects fall with the same acceleration unless air resistance or some other force acts on them. He argued that the air resists an object traveling through it. If the material is dense and its surface area is small, the air resistance is quite small as compared to the gravitational force. Air resistance can be neglected while studying falling stones, metallic blocks, etc. Since the acceleration of an object is the rate of change of its velocity, so there is no effect of its mass. Therefore, when a heavy object and a light object are dropped from the same height, both would reach the ground at the same time. To find the truth, he did experiments with bodies rolling down inclined planes and measured the value of acceleration, which was close to the more accurate value of acceleration due to gravity obtained later. In 1686, Newton formulated his well-known law of gravity, according to which every particle in the universe attracts every other particle with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. He established a relation for the force of gravitation and concluded that the Earth attracts every other body lying near or on its surface towards its center. The term gravity is used for the force of attraction exerted by the Earth on the body. When a force acts on a body, it produces acceleration. Therefore, a body under the effect of gravitational pull must accelerate. For example, if we throw a ball upwards, its speed decreases till it reaches the highest point, and if we throw a ball at an angle, its speed changes throughout its motion. It shows that whenever an object falls freely near the Earth's surface without an external force, that is, under the influence of the Earth's gravity only, then it is accelerated. The acceleration produced in the motion of a body under the effect of gravity is called acceleration due to gravity. It is denoted by small g. Let us consider the Earth as a solid sphere of uniform density, and the entire mass of the Earth is concentrated at its center. If an object of mass m moving freely near the Earth's surface, neglecting the air resistance, the only force on the object is due to gravity. Magnitude of the force of gravitation on the object is g times the product of the mass of Earth and mass of the object upon the square of the distance between them, that is, the radius of the Earth. By using Newton's second law of motion, the acceleration of the object can be obtained as the ratio of the force due to gravity and the mass of the object, which is equal to the product of the universal gravitational constant and the mass of the Earth upon the square of the Earth's radius. This is the expression for acceleration due to gravity at the surface of the Earth, which is usually denoted by the symbol g. In general, acceleration due to gravity on the surface of the Earth is equal to the gravitational force per unit mass, and its direction is always towards the center of the Earth. This is a very significant and quite remarkable relationship. Here, acceleration due to gravity g is measurable. Here, it can be noticed that acceleration due to gravity does not depend on the mass of the object on which the gravitational force is acting. For all other forces, acceleration depends on the mass of the object on which the force is acting. That is why the value of acceleration due to gravity does not depend upon whether the object falling under gravity is a light one or a heavy one. Knowing the mass of the Earth and the radius of the Earth, the value of g can be calculated as 9.81 meter per second square. On the other hand, knowledge of the values of gravitational constant, acceleration due to gravity, and the radius of the Earth enables us to estimate the mass of the Earth. This is the reason when Cavendish measured the value of universal gravitational constant, there was a popular statement that Cavendish weighed the Earth. Acceleration due to gravity on the Earth's surface is 9.81 meter per second square. But when we go above the Earth's surface, the value of g decreases. Because at a height h from the Earth's surface, mass of the Earth remains constant, but the linear distance between the object and the center of the Earth increases. The acceleration due to gravity at a height h will be equal to g into mass of the Earth upon the square of the distance of the object from the center of the Earth. On the other hand, when we go deep inside the Earth, the value of g should increase. But the situation is different, as the value of g again decreases. In this situation, the gravitational force acting on the object at depth d is due to the effective mass of the Earth's shell of radius re minus d. Let's see an interesting situation. Suppose we have a tunnel passing through the center of the Earth, starting from the North Pole and ending at the South Pole. If we drop an object in the tunnel from one end, the acceleration due to gravity decreases as we go down towards the center of the Earth. And at the center of the Earth, it becomes zero. But at the center of the Earth, the object has a maximum kinetic energy and hence it moves forward. Moment the object moves from the center of the Earth towards the other end, the acceleration due to gravity starts increasing. Thereby, the velocity of the object starts decreasing. When the object reaches at the other end of the Earth, its velocity becomes zero. Therefore, it returns back. In this way, the object would show to and fro motion in between the North Pole and the South Pole. Measured value of acceleration due to gravity is different from the actual value due to some natural factors such as constitution of the Earth, shape of the Earth, and rotation of the Earth. For example, in the formulation for acceleration due to gravity, the Earth was assumed as uniform and stationary sphere. But our Earth is not a sphere. It is an ellipsoid. Its equatorial radius is greater than polar radius by 21 kilometers. Because of this, acceleration due to gravity is greater at poles than at the equator. Since the radius of the Earth does not change much over its surface, thereby acceleration due to gravity more or less remains constant on or near the Earth's surface. Because of this, when an object is moving vertically up or downward under the gravity, its motion is similar to the uniform acceleration motion. And all the equations for the uniformly accelerated motion become valid by replacing acceleration A by acceleration due to gravity, that is g. Since direction of acceleration due to gravity is towards the Earth's center, therefore, when the object is moving upwards, value of g becomes negative. And when the object is moving downwards, value of g becomes positive. Let's solve some problems. A ball is dropped from a building 196 meters high. How long does it take to reach the ground? Here, the height is given from where a ball is dropped, which is initially at rest. Time required by the ball to reach the ground can be measured by second equation of motion as shown. In the next problem, a stone is dropped from the top of a hill 1960 meters high. What is the velocity when it has covered 1000 meters? Find the velocity when it hits the ground. Here, the height is given from where a ball is dropped, which is initially at rest. By using third equation of motion, velocity after covering the distance of 1000 meters comes out to be 140 meters per second. When the stone reaches the ground, its velocity comes out to be 196 meters per second. By knowing the acceleration due to gravity, one can measure the weight of an object. Generally, mass is commonly referred to as weight. For example, we say that an object weighs 1 kilogram, even though kilogram is a unit of mass. In fact, weight and mass are quite different quantities. Mass of an object is the quantity of matter it contains. The mass of a body is defined in two different ways: inertial mass and gravitational mass. Inertial mass is the measure of an object's resistance to changing its state of motion when an external force is applied. In other words, when a body is in translational motion under the effect of an external force other than gravity, the mass of the body measured is called its inertial mass. On the other hand, when a body is under the effect of gravity in the absence of motion, the mass of the body measured is called gravitational mass. Weight is the measurement of the strength of gravitational force on the object. That is, how heavy it is. We know that the unit of mass is kilogram, but the unit of weight is kilogram weight, and SI unit is Newton. The weight of a body of mass m is equal to the product of mass with acceleration due to gravity. Mass is an essential property of any material object, and therefore, for a material object, mass can never be zero. It is not affected by the presence of other objects. An object has the same mass wherever it is. It does not vary with the change in temperature, pressure, or location of the object in space. Whereas, weight of an object becomes zero at the center of the Earth, which also suggests that weight is not an essential property of the object. Weight or the gravitational force can change with location, as well as it varies from place to place on the Earth's surface and with distance above or below the ground. For example, if you're lucky to travel to Moon someday, you will find that your weight is less on the Moon than on the Earth, though your mass remains unchanged. It is 1/6 that of the Earth. For example, if the mass of a boy is 25 kg, then his weight on the Earth is 25 kg weight or 245 Newton. Whereas on the Moon, the mass of the boy still remains 25 kg, but his weight becomes 40.5 Newton or 4.1 kg weight. The weight which we actually measure is not the downward force of gravity, but an upward force exerted by the surface we stand on.